This is lesson 7 and 8. I'm putting both of these lessons together. It is on magnitude and estimating quantities. So first we're going to take a look at powers of 10. So meaning just if 10 is our base, and then looking at if we have exponents on that, what that looks like. So let's start with 10 to a power of -5, okay? We know from our work with exponents that this means I don't actually have 5 tens on the top, I have 5 tens on the bottom. 1, 2, 3, 4, 5, okay? And so if I actually multiply that out, I'd have 1 over 100,000, which if I actually calculate out, I don't think I know that off the top of my head, 1 divided by 100,000. .00001 is that. Let's try 10 to a -4, which we know is 1 over 4 tens. So that's 1 over 10,000, and that's going to equal 3 zeros and then a 1. Okay, let's keep going. You can start working ahead of me if you're already seeing a pattern. One over 1,000 is 10 to a -3. 0.001, 10 to a -2, 1 over 2 tens, which is 1 over 100. And I know it's 100 because I have 2 zeros here, 2 zeros here. 0.01, 1 over -1, 1 over 110, which is just 1/10 anyways, 0.01. Now let's go positive. I'm going to have to erase this just so I have space, but you can keep working. 10 to a 0 means we have 0 10. So that's actually just 1. 10 to a positive 1 means we have 1 10. 10 squared means we have 2 tens multiplied by itself, so that's 100. 10 cubed means we have 3 tens multiplied by itself, so that's 1,000. 4 tens multiplied by itself for 10 to the 4th, and 5 tens multiplied by themselves for 10 to the 5th. Alrighty. And hopefully you're seeing a pattern here of what's going on. Okay. So let's try some more extreme examples. Hopefully we were seeing that when we had a negative exponent, you're getting something smaller, and when you have a positive exponent, obviously you're getting something bigger. So let's say I had 10 to a -7. Okay. If you look back at the other ones, because I don't want to have to actually go through the whole thing of 1 over 7 tens and multiplying that out, you might be looking at the ones we just did and said, well, whenever you have a negative, you have 1 less of that many zeros and then a 1. Okay, so what that would look like is you have 6 zeros, 1, 2, 3, 4, 5, 6, and then a 1. Because this -7 says that the 1 is 7 decimal places, 1, 2, 3, 4, 5, 6, 7, behind the decimal. Okay, so let's say I had 10 to a -20. Okay, you can actually write this out if you want, but what this really means is that we're going to have 19 zeros and then a 1. And again, you can write that out if this doesn't really make that much sense to you. if I had 10 to a negative 34, it's going to be 0.33 zeros and then a 1. Okay? For those of you who do want to write it out, I can go ahead and take some time to do that, and the rest of you can skip ahead. So 10 to a negative 20, that would look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then you have that 1. Okay? Same thing for 10 to a negative 34. That means we have 0 point and then 33 zeros because it's 1 less than this number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, good. 23, 24, 25. Are we off the screen? Not yet. 26, 27, 28. Getting there. 29, 30, 31. Almost off the screen. 32, 33. And then we have that 1. Barely made it on the screen. Sorry if it's messy. Okay. So we have this pattern here. If it's negative, if the power is negative, you have 1 less zeros. Okay? So 7 became 6 zeros, 20 became 19 zeros, and 34 became 33 zeros. Okay? You, of course, can always do the long way, putting 1 over that many tens, multiplying it out, changing it over to a decimal, but I think just knowing this rule will help a lot. Okay? And if you always forget this rule, you can always just look at really small examples to help you remember that. So the fact that we all know 10 to a negative 1 is 1 over 10, and we all know that that is 0.1. Okay, so 1 less than 1 is 0, so there's no zeros here. Okay, so just, if you're forgetting this rule, try out a simple one in your head, and that will remind you that, oh, we don't have 1 0, we have 0 zeros, because it's 1 less. Okay, now let's take a look at what's going on with the positive powers. So take a look back at the ones we already worked through, see if you can see what's going on there. With the positive powers, hopefully you notice that that's exactly how many zeros you have. So with the negative, it's 1 less, but with the positives, it's how many zeros you need. So let's take a simple one that we can already calculate. If we had 10 to a 6 power, that means I'm going to have 1 and then 6 zeros. 1, 2, 3, 4, 5, 6. Okay. If I have, let's go a little bit more extreme, 12, that means I'm going to have a 1 and then 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, let's keep going more extreme. Let's think of a number. 76. 10 to a positive 76 power means you're going to have a 1 and then 76 zeros. Good. You can write that out on your notes if you want to. I'm not going to. So 10 to a 76 power means you have a 1 followed by 76 zeros. Okay? Let's go a little bit more realistic again. 10 to a, I don't know, let's do, what's something realistic? 24. 1 followed by 24 zeros. And if you actually want to write that out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 4, and there you go. I don't even know what to call that number. There's thousand, there's million, there's billion, there's trillion, and I don't even know the names that's past that. Okay? So now you'll see that we're starting to work with really, really big and really, really small numbers. And that's one of the reasons that we always start working with powers of 10 instead of writing these numbers out or saying the full-blown version of these numbers. It's a lot easier to say 10 to a 24 than it is to say 1, I don't know, floppy trillion or whatever this is actually called. Okay? So powers of 10 is actually really powerful in talking about really big and small things. Let's now get some vocab in. So powers of 10s are really nice because we can talk about how big or small things are. And there's a word for that. It's called magnitude. Magnitude is how big or small something is. And you can actually use powers of 10 to describe something's magnitude. Okay? So you might hear researchers talking about how atoms are, I'm going to make up a number because I don't know the actual one, like maybe 10 to a negative 24. Because saying that actual number is really time consuming. So it's easier to think in terms of the magnitude in those powers of 10. Okay. What if I had something times that power of 10? And some of you might look at this and be like, I've seen numbers like that, and you probably know the name of it. That's actually our next lesson. That's lesson 9. But it's okay if you're thinking, oh my God, this is scientific notation. You are correct. This is scientific notation. But if you don't know what I'm talking about, don't worry about that. That's our next lesson. Okay? So what if I had a number times a power of 10? What is this actual number? You see this a lot when you're reading science magazines and stuff like that. They'll talk about, oh, something was 3 times a power, or times 10 to a 30 power. Well, what does that actually mean? So here we have 2 times 10 squared. So we still have a 2. That hasn't gone anywhere. This 10 squared really means we have 100, right? Because that is what 10 times 10 is. So, and then what's 2 times 100? That's 200. So, right now it might not seem like this is shorter, but as I go through more examples, you'll see that writing it in a form like this can actually be a shorter way of writing really big or small numbers. Okay? What if we had 3 times 10 to a 4th? Well, that's 3 times 1 followed by 4 zeros, just like our rule that we saw earlier. So that's 10,000. So it's 3 times 10,000, so that's 30,000. And now it's looking like this is a little bit more realistic to write 3 times 10 to the 4th than 30,000. What if we went bigger? What if I did, let's do 7 times 10 to the 7th. Okay, now this looks nice and tidy, but let's expand it out. 7 times 1 followed by 7 zeros. So this is 10 million. So if I multiply this out, that's 70 million. And this number right here is longer than this. Not in actuality, but writing it out takes a lot longer than just writing this little tiny thing. Okay, let's go even more extreme. Let's do, how about 4 times 10 to the 11th power? That means I have 4 times a 1 followed by 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And what number is this? This is, what's that? That's thousands, millions, billions. So this is 100 billion. Not a word we use all the time. 100 billion. So that makes this 400 billion. Ooh. That definitely took longer to write out than just 4 times 10 to the 11th. Okay. So instead of saying you're a 400 billionaire, you can say, oh, I'm a 4 times 10 to the 11th there. So it works really well for really, really big numbers, and you can try out even bigger examples if you want to. Now let's look at smaller numbers. Okay, and you should be thinking, okay, if we're talking about small numbers, we're talking about powers of 10s that are negative. So let's try out a very simple one. What if I had 2 times 10 to a negative 3? Well, we still have the 2, and it's going to be 2 zeros, because we have a 3 followed by a 1. Okay? So that becomes 0.002. So that 2 thousandths. Okay? So right now, again, because we're talking, this is a pretty small example, this may look about the same as this. But let's make it more extreme, and we can start saying that this is definitely more efficient. What if we had 6 times 10 to a negative 6? Oh, we got 6. Our decimal is followed by 5 zeros, because it's 1 less than the 6. Okay? Multiply that out, and when we're multiplying it out, really all you have to do is take that 6 and put it where the 1 is. Okay? So this number, writing this out, takes longer than it is to write this. Okay, let's do one more example, more extreme. 9 times 10 to the, let's do negative 14. You're already thinking, oh, this is going to be a pain. And probably will be. So let's work through it together. 9 times, then we have 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, followed by 1. Just that in general is already pretty nasty. Let's actually multiply it out. So replacing the 1 with the 9. So we still have our 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, followed by that 9. Okay, so scientific notation, or just this method of using the magnitude times a number, is a much more efficient way of writing really, really small numbers. And honestly, that number is actually not that small when you think about sizes of things in cells, in atoms. There are many, many way smaller things than that number. Okay. And you have this on your paper that there's always a power 10 bigger than a number, and there's always a power 10 smaller than a number. Okay. And the great thing about that is you can use it to estimate numbers. And the important thing about estimations is you use them whenever you don't care about the actual number. I may not actually care about the fact that I have, 232 markers in my cabinet. I just want to know that's like, okay, I have about 250. That's a good amount for me to estimate when I'm thinking about I have these projects coming up and stuff like that. Okay? So you use estimation whenever you don't care about the actual number. Okay? So what if I had a number, let's do 152, okay? My computer keeps falling asleep. So if I had a number of 152, what's a power 10 less than this, okay? And while we're starting out, it's okay to just kind of throw things out and then eliminate them. So let's throw out a couple. We have power of 1, power of 2, power of 3, power of 4, okay? Now, 10 to a power 1 is just 10. That's definitely smaller than that, so let's keep it on the board for now. 10 to a power of 2, well, that's 100. Oh, that's also smaller than this, so we can get rid of 10 to a power of 1, because that's too small. This is pretty close, so I'm starting to think maybe this is the one that's bigger. Well, 10 to a power of 3 is one with 3 zeros, and oh, that is bigger, so I can actually get rid of this one. So this is the power of 10 that's smaller, and this is the power of 10 that's bigger. Okay? And some of you might be looking at this and be thinking, there's got to be an easier way of doing this instead of doing process of elimination. And you are absolutely correct. Okay? Guess and check is always a good method, but of course we want to be more efficient with our work. We don't want to do more work than we have to. Take notice of this. There is 3 digits here. Okay? Now the one that's smaller is 10 to a power of 2. The one that's bigger is 10 to a power of 3. Okay? So you want to be thinking of, oh, there's 3 digits, so something 10 to a power of 3 is going to be bigger because you have 3 zeros. So there's actually 4 digits here, where something with the power of 2 is also 3 digits, so that's going to be smaller. Okay? Let's take a look at another example so I can show you what that really looks like. So let's talk about the number 93,825. Okay? So maybe I'm still not quite that good at this, so I'm going to take a look at 10 to the power of 5, because there's 5 digits here. So I'm going to take a look at 10 to the power of 5. Well, 10 to the power of 5 is 1 followed by 5 zeros. So that's 100,000. Oh, that's bigger. So if I go 1 down, that's smaller. Okay, so let's look at another example now that we're getting a little bit better at this. Let me think of a number. Let's say I have 1,375. Okay, there are 4 digits there. So 10 to the power of 4 is going to be bigger, and 10 to the power of 3 is going to be smaller. Okay, so let's get up here a general rule for this. Bigger power of 10s have the same power as the number has digits. So like how this had 5 digits, so the bigger one had a power of 5. Or that one had 4 digits, so the bigger number had a power of 4. Okay? All right, let's write the rule for smaller. Smaller powers of 10 have 1 less power than the number of digits. So this was 5 digits. The smaller one has 4 as an exponent. That one was 4 digits, so the smaller power has an exponent of 3. Okay? And it might be hard to remember both of them, so I'd say just remember the bigger one, and then it's easy to go, well, obviously the smaller one is 1 less. Okay? But that's just me. You can remember both if you want to. Now, what if we had negative powers? So what if we're talking about decimals? Do these still hold up? Well, let's take a look. I'm going to erase my examples, leaving my rules up here. What if I have 1, 2, no, let's make this something different. Let's keep it simple. 0.02. So what's the power that's below this, and what's the power that's above this? So let's use guess and check because we haven't dealt with decimals yet, so it's easy to go back to what we thought before. So if we had, let's try the same thing. So I'm just gonna guess 10 to a negative 2. There's 2 positions behind. I'm gonna guess that 10 to a negative 2 should be one of the numbers, bigger or smaller. So let's expand this and see which one it is. 10 to a negative 2 we know means that you have 1 0 and then a 1. Oh, that's less. So do we need to go up as in make it 10 to a negative 1, or do we want to go more as in 3? Well, let's try out both of them and see which one it is. So here we have 0.1. Well, that's definitely bigger. 0.001. Oh, that's smaller. So this is the one immediately bigger, and this is the one immediately smaller. Okay? So it seems like our rules only apply, these ones that we wrote up only apply for the positive powers. Okay? So make a note of that because we're going to have to write up some new rules for our decimals for our negative exponents. Okay? And there's obviously a place for this on your paper. So let's write up these new rules for these negative exponents. So the bigger one has an exponent 1 less than how many places? Now is that the way we want to write it, or maybe we want to write it that the bigger one has as many zeros as it has? That's probably the easier way of thinking it. So bigger power of 10 has the same negative exponent as the number has zeros. So here the bigger one was negative 1, and here there's 1 0. So then the 1 less is 1 less. Okay? You guys have to remember that 1 less when you go negative, the actual number gets bigger because you're getting more in debt. Right? So like if you owe me $5 and you have less money, you'd end up owing $6. So the smaller power of 10 has 1 less. How do we want to say this? 1 less than the bigger one. Or you can say it's the negative power of 1 more than the zeros. But I think that's probably harder to say. So let's just start with the bigger one, and then you can always find the smaller one because thinking it's 1 less. All right. So let's try another example and see if these hold up. And remember that these are for the negative exponents. All right, let's try another example. So let's start with the bigger power. So the bigger power of 10 has the same negative exponent as the number of zeros. So this one should be to a negative third power, should be the bigger. Okay, well, let's take a look at that. That means we have 0.2 decimals and a 1. And yep, that's definitely bigger. 0.001 is bigger than 0.0003. And so now we need to think the smaller power has 1 less than the bigger power. And remember, when we go less with a negative, it becomes more negative. So the actual digit, the actual number becomes more. Okay? So this should be the smaller one. And let's test it out. Let's make sure it is correct. So this would be 3 zeros followed by a 1. And yeah, that definitely is. So you have to remember, when you're dealing with decimals, you really want to pay attention to that first digit. These other ones are kind of talking about how close we are getting to this next number. So these are like, hey, we're actually pretty close to this being a 4, but we can kind of almost ignore them. We really only care about this first number. And so when we compare this one to this one, they have the same amount of decimals, but 3 is bigger than 1. Okay? So this rule that we wrote holds up again. How about we try one more example, because I know it's a little bit weird with the decimals. Let's try one more. Now, again, remember, we care about the first actual number. We don't care about how many digits there are. All these are saying is how close we are to turning this into a 2. Okay? So the bigger power 10 has the same negative exponent as the number of zeros. So we have a negative exponent in the same amount as the number of zeros. Well, there are no zeros, so that would be a 0. And some are like, well, there can't be a negative 0. And you're right, so let's rewrite that as 10 to a 0. So, but 10 to a 0 is 1. Is that bigger than that number? Absolutely. Any fraction is less than 1, so this is definitely bigger. Let's try our smaller one now, which means we're going to need 1 less than that number. What's 1 less than 0? Negative 1, which actually is 0.1. And this number is less because this number has all these other numbers to back it up, saying that, well, actually this is closer to 2, and this one's just regular 0.1. So this one is smaller. So once again, this rule that we wrote holds up. Now we're going to take a look at using magnitudes, powers of 10, to estimate really, really big numbers so that we can compare them. Because it makes it so your calculations, you can deal with just the powers of 10, so you don't have to deal with the real numbers, because sometimes they're really annoying. 15,706. And yes, I looked this up, so this is accurate as of like a couple days ago. So the average household just owes $15,000 from credit cards. We're not talking mortgage and all student loans, all that extra stuff, just from credit cards, okay, that's a lot of money. Now, the national debt, what our country owes, and this has probably gone up since I looked it up, so this was accurate as a couple of days ago. Gosh, what is that number even? That is 18,388,603,567,287 as of a couple days ago, so it's probably actually gone up a couple thousand since then. So, if I wanted to say how many times bigger is this debt than your household credit card debt, yes, we can pull out our calculators and plug these in, but some of our calculators actually can't even hold that many numbers on our screen, so you'll probably get an error message, or you get this really nasty number that you don't even know what it means. And let me just put this on the board. Please don't write it down. The actual amount, I mean, you can write this on your notes if you really, really want to, but oh my goodness. And there's a nasty decimal after that. So it's actually, what number is this? This is 1,170,801,194 point stuff times bigger. Not just like amount bigger, times bigger. So you have to multiply our debt by this to get the national debt. Whew. We're definitely talking about big numbers here. So thank goodness we know how to use powers of 10 to make these numbers look a little bit smaller, more manageable. So let's change these numbers to being powers of 10. Now, again, this is going to be an estimate. So that's why we can change these to being powers of 10, because we don't actually care about the actual amount. We just want like a good estimate. Okay? So let's change 15,706, our household credit card debt, to a power of 10. And sorry that I'm off the screen. So we need to think, I'll use a different color so it shows up more clearly. We need to think how many digits are here. So the easiest thing to think about is just to round it. Just round it to the nearest power of 10. So I'm going to just round it down to 10,000. And I know you're thinking, well, that's actually a really low estimate of that amount. And that's okay. We're doing an estimate. So this can be changed to 10 to the power of 4 because there's 4 zeros. Okay? Now let's change this national debt. This national debt, you want to think that we're going to be rounding it down again because we just want to change it to the power of 10. So we're actually going to be changing it to whatever 10 trillion. We're actually going to be rounding it down to 10 trillion. Okay? So if we change that to a power of 10, which, I mean, when you're dealing with these numbers, is a lot better, a lot easier to deal with just a simple 10 to some power. Well, we got to know how many zeros are there. There's 3, 6, 9, 12, and one more makes 13. So there's 13 zeros. Okay, so now doing this, it's a lot easier to say we're dealing with 10 to the 13 and 10 to the power 4 opposed to these actual numbers. Okay, just in the amount of time it takes to say them, it's a lot faster. Okay, so we're going to be comparing 10 to a 13 to 10 to the 4. And a lot of you are looking at this like, oh, I know that kind of problem. We've been doing a lot with those kinds of problems. And that's exactly why we do exponents before these lessons, because those same things apply. So now that we change those to powers of 10, they're just exponents, and we can just do the quotient rule right here. Because we're just taking that big number, dividing it by that small number to get how many times bigger it is. So 10 to the 13 divided by 10 to the 4th. By our quotient rule, we do 13 minus 4. So that's a 10 to a power of 9. So the national debt is 10 to the 9th power bigger than the credit card debt. Now, again, that was an estimate. Let's take a look at how close that actually was to the actual. Now, 10 to a power of 9 means we have a 1 followed by 9 zeros. And take a look at that. That's actually pretty close. We got the same number up front, same amount of space essentially. It's like you just took all of this and erased it. So it's actually pretty close. That's a pretty good estimate, especially considering that I know most of you probably were not comfortable with the fact that we rounded both numbers down by so much. But that's a pretty close number for how many times bigger it actually is. I have one more example of these. I promise the numbers are smaller. I just want to show you why we use powers of 10, because when numbers are ridiculous, it's easier to work with powers of 10. So here we have the population of some city. I looked this up way too long ago, so I don't remember the city. In 1723 was 7,248. Okay, I don't know what city this was. If it helps you, you can say it's Santa Rosa, or maybe you want to say it's like Shanghai or something like that. I really don't care. Population of some city in 1723 was that number. Then the population in that same city in 1870 was, of course, a lot more. 942,292. Okay, so these numbers aren't as big. We could just throw that into our calculator if we wanted to. But if I don't have a calculator, I can just do the powers of 10, just like before. I purposely chose numbers that are pretty big numbers as far as the first digits. Because we know from whenever we learned rounding, like 3rd grade, 4th grade, that if that number is bigger than 5, you can round up. So what I would actually suggest, instead of just rounding this down to 1,000, because we know that would be a really low estimate, let's round this up to 10,000. Okay? Which then if we change to power of 10, There's 4 digits there. This next one, again, 9 is really, really close to it becoming 10. So let's just round this whole thing up. So we'll round it up to 1 million. There's 6 zeros there, so it's 10 to the power 6. Now that they're in much simpler form, it's really easy to compare them. So let's calculate how much bigger, how many times bigger the population was in 1870 than it was in 1723. So we're going to take our bigger number, 10 to a 6, put it over our smaller number, and we just have the quotient rule again. 10 to a 6 minus 4, so it's 10 squared. Okay, and since 10 squared is a really small number, if you wanted to, you could be like, all right, it's 100 times bigger. And there you go, that's it. So comparing numbers, actual numbers, you can just convert it to their magnitude to the power of 10 that they're closest to, divide them up, and then that's how many times bigger that bigger number is than that smaller number. Okay, and we'll go over, I think, at least one more example of this in class, if not two. So we're going to convert some numbers to be written as a number times a power of 10. So I'm just going to put up some numbers, and I'm going to show you how to convert them to being a number times a power of 10. That's the same format I showed you earlier, and that's actually working towards our next lesson, which is scientific notation. So for a lot of you, you've learned this before, so it'll be simple, and for others, it will not be easy, but that's okay. We're just learning it, starting the basis of it now, then we'll really be learning it in the next lesson. Okay, so what if we had 0.003? Okay, well, that first number, let's just take that 3, okay? Because we can't just get rid of that 3. We're not making an estimate. We're actually doing an actual amount. We're just converting how it looks. So we got a 3, and we know we need it times the power of 10. But the question is, what power goes there? Well, I'm thinking it needs to be a negative power because this is a decimal. But then, what should go there? Well, if you remember back to our rule, the power of 10 was 1 less than the amount of zeros. So there's 2 zeros, so if I do 1 less, it should be 3. The other way of thinking about this, and for some of you this will be the easier way of thinking about it, and this is actually how I normally think about it, is think about how many times I need to move the decimal so that this becomes a regular 3. So like if I move the decimal once, twice, 3 times, then that 3 becomes a regular 3. Okay? Let's take a look at another example. Maybe I'm going to turn 0.00007 into a number times a power of 10. Well, we got to keep that 7. We know it's times a 10. Then what should that power be? Now we could do the rule way of counting up, well, there's 4 zeros, so I need to go 1 less, so it needs to be -5. Or we can count up how many places, and that's 1, 2, 3, 4, 5. So either way, you get to that -5. Let's try positive numbers now. What if I had 80,000? Okay, well, let's keep that 8, and then it's times some power of 10, so we're almost there. We're just missing that exponent. Then you can think back to our rule before of how to expand it as, well, there's 4 zeros, okay? So we can put a power of 4, or we can count the decimals again. All whole numbers have a decimal right at the end, even if we don't write it. So you can think, well, how many times do we have to move it forward to make this 80,000 just a regular 8? And it would go 1, 2, 3, 4 times. So once again, counting that decimal holds up. Let's try another example. Let's try, I don't know, 7 million. Okay, keep that 7. And we need times 10 to some power. You can either look in this and be like, there's 6 zeros. Alrighty, let's write a 6. Or, which again, remember that only works with positive exponents, so these have to be numbers greater than 1. Or sorry, greater than 0. Or we can count the decimals. 1, 2, 3, 4, 5, and 6. So that holds up again. Here comes the part where we get to see how our calculators tend to fail us when we are working with these numbers. And this is one of the reasons why I always tell you, yes, you can use your calculator, but it probably won't help you. So let me erase the board and go ahead and put this number into your calculator. Put 10 to the 40th power into your calculator, which for some of you means you need to put in 10, and then there's like a little caret button, and then you push in 45. For others of you, that means you push 10, and then there's this little symbol that says y to an x, and then you push in 45. Okay? And I can always help you with this if you just really don't understand what I mean or you don't have access to a calculator. Don't worry about it. You can leave this part blank and just write down what we show you at the end. So if I put in 10 to a power of 45, I get, and everyone's calculator is different. My personal calculator right here just says 1 decimal and you got a 45. Well, that doesn't look like the same thing. Some of your calculators will say 1e plus 45. Well, that doesn't look like the same thing. And some of yours will just give you an error message. Okay? So just to let you know how to distinguish what your calculator's saying, you do need to get familiar with your calculator if you're going to be doing stuff like this. Of course, I'm showing you all the ways how to do it without your calculator. But if your calculator is giving you this, it's showing you scientific notation. It's showing you that this actually means 1 times 10 to a 45. That's about 10. Okay? Same thing down here. This is saying, oh, we have a 1 times 10 to a 45. And we know that 1 times 10 to a 45 is the same thing as just 10 to a 45, because multiplying things by 1 doesn't change the identity, doesn't change what we're talking about. Okay? So this is just to get you familiar with the fact that your calculators are going to start saying different things than what you think they're saying. They are saying 10 to a 45, just not in a way that you're familiar with. So part of this unit is getting used to how technology represents powers, really, really big or really, really small powers. Let's try one other and just see how our calculators fail us. Let's try a negative exponent. So go ahead and put in 10 to a negative 12 into your calculator and see what it comes up with. Some of your calculators can actually do it. Some will say 1 decimal negative 12, which means, oh, hey, I have 1 times 10 to a negative 12. Others will say 0. Because your decimal is telling you that this number is so small, let's just chalk it up to 0. It's too small. We don't care anymore. It's just 0. And some of yours will just say error. And that's just what it's going to say. So you want to get familiar with your calculator so that when you plug these things in, you don't just write this down and think that that's an okay answer. Okay? We're dealing with these sort of numbers now. I don't want to see these unless it's asking you to do that. And that's it for lessons 7 through 8.